discuss the concept of transactions. Concept of transaction, what are the different states of a transaction, and implementation of atomicity and durability, and what you mean by concurrent execution of data. Then serializability, recoverability, implementation of isolation, transaction definition in SQL, testing for serializability. These are the topics which we are going to cover under transactions. Today we are going to discuss what are transactions and what are the different states of a transaction. Okay. The concept of transaction is a transaction is a unit of program execution that accesses and possibly updates various data items. Various data items are residing in the database, and you are going to act. For example, suppose that you are doing a train ticket reservation, then that process is having a number of steps. For example, you are searching, then you suppose that you are pressing the booking button, then definitely there should be a seat available, and when you have searched for tickets that was available, but at the point of reserving tickets that may not be available. So in that case it should be there, and a transaction means a number of steps. That means initially that we will discuss. Okay, a transaction must see a consistent database. Suppose that you are transferring an amount to your friend, and at the time of deducting that amount from your bank account, at the same time your friend's account should be updated with the amount. Okay, suppose that the bank has reduced your amount, decreased your amount, or debited from your amount, and before crediting that to your friend's account, suppose that there is a crash, that database is said to be inconsistent. So a transaction must be in a consistent state. During transaction execution, the database may be inconsistent. When the transaction is committed, database must be consistent. Two main issues that deal with that means in between there may be failure of various kinds, such as hardware failures and system crashes, concurrent execution of multiple transactions. That means if you are using a database, a central database, a number of different processes or different person located in different parts of the different locations may be using a database at the same time, so there should be concurrent execution of multiple transactions. These are the ACID properties and the desirable properties of a database. To preserve integrity of data, the database must ensure atomicity. That means either all operations of the transaction are properly reflected in the database or none. Suppose that you have debited an amount from an account, and suppose that in between, before crediting that to another account, suppose that there is a failure. In that case, that database is inconsistent. That means either you do the debit and credit at the same time, or you otherwise it has to go to its before the previous consistent state. That means that is atomicity. Either all operations of the transaction are properly reflected in the database or none. Consistency means execution of a transaction in isolation preserves the consistency of the database. That means if you are defining a transaction, either it has to execute that transaction as a whole, or in between, if there is a failure, you have to revoke that. That means at the before that, some consistent state may be there. Before starting that execution, you have to revert that consistent state. Okay. Isolation. Although multiple transactions may be executing concurrently, each transaction must be aware of other concurrently executing transactions. That means a number of transactions are executing at the same time, and each transaction must be aware of other concurrently execution transactions. executing transactions. Intermediate transaction results must be hidden from other concurrently executed transactions. That is, every pair of transactions TI and TJ, either TI should appear before TJ or TJ should appear before TI. That means as far as TI is concerned, TJ should execute either before TI or after the execution of TI. As far as TJ is concerned, TI should appear either before the execution of TJ or after the execution of TJ. Then durability. After a transaction completes successfully, the changes it has made to the database persist even if there are system failures. Suppose that you have changed, or a transaction has changed the content of the database, then durability means even if after this some crash, some system failures occur, then that should be durable. That means that database should persist. That is the meaning of durability. Example of fund transfer. Transaction to transfer $50 from account A to account B. First transaction is reading the value of A. Then second statement is you are debiting 50 rupees from A. Then write the value of A. Now after statements 1, 2 and 3, the value of A is decremented. Now fourth statement, value of B is read, then B is incremented by 50 and then writing the value of B. That means writing the value of A, that means debiting has taken place in the statement number 3 and crediting is done, or that is reflected after the execution of 6. Suppose that there is a system crash, or suppose that there is a data failure or something like after transaction number 3 and before 6, what will happen? The database become inconsistent. Consistency requirement is the sum of A and B is unchanged by the execution of the transaction. That means before and after transaction, $50 has been debited from one account and credited to another account. In either case, A plus B before and after the transaction should be the same. Then atomicity requirement. If the transaction fails after step 3 and before step 6, the system should ensure that its updates are not reflected in the database, else an inconsistency will result. Durability requirement. Once the user has been modified that the transaction has completed, the updates to the database by the transaction must persist despite failures. That means after the sixth statement, the transaction has been completed. Once that transaction is completed, then that should be reflected on the database even if there is a system failure. That is durability requirement. Isolation requirement means if between step 3 and step 6, that means after updating the value of A, if you have not updated the value of B, another transaction is allowed to access the partially updated database. That means A plus B remains the same. Now your value of A you have updated, but B is not updated. At that point in time, some other transaction may be accessing that value A, but that is not consistent. Can be ensured trivially by running transactions serially, that is one after the other. That means at a point in time, no transaction is allowed to run concurrently. If concurrent transactions are there, then that should be in a serial fashion. Serializability we will discuss later. However, executing multiple transactions concurrently has significant benefits, as you will see. Transaction state. A transaction is active. That means initial state. The transaction stays in this state while executing. That means when a transaction is executing, we say that the transaction is active. Once it has completed the execution of transaction, we call it as partially committed after final statement of that is executed. For example, in our fund transfer, after the sixth statement is executed, we say that it is partially committed. Failed means after the discovery that normal execution can no longer proceed, that means it is failed. Aborted means after the transaction has been rolled back and database restored to its previous value. That means when you are doing some transaction, suppose that if you want to transfer an amount of say rupees 10,000 to some other account, and when you are trying to deduct an amount of 10,000 from A, suppose that if there are insufficient funds, in that case you have to go back to your previous consistent value. That is called aborting the transaction. Two options after it has been aborted: restart the transaction. That means only if it has aborted, you can start from the scratch. That means restart the transaction or kill the transaction. That means you are not going to do the transaction. Committed means once you have successfully completed the transaction, then we call it as partially committed, and at the end of the transaction you are going to have a committed statement. That means once it is committed, there is no possibility of revoking or abortion. Okay, that is we call it as committed. See, this is the different life cycle stages of a transaction. That means transaction is either active or it is partially committed, failed, committed or aborted. That means if a transaction is executing, that is in an active state, and after the last statement of the transaction it will enter a partially committed state, and if there is no point or if there is no possibility for revoking, then we will enter committed state. Once it is committed, then there is no possibility of reverting back to its previous consistent state. Even if it is in a partially committed state, it can fail and that can be aborted. Okay. If in an active state, suppose that there is some problem, or for example, suppose that if you are reducing, if you are trying to have a fund transfer, and if you are trying to debit some amount, then suppose that there are insufficient funds, then the transaction has to be aborted. In that case also it is coming to the failed state and it will be aborted. That means if a transaction can either be committed or it should be aborted. So that is all about transactions. And implementation of atomicity and durability can be implemented like this. The recovery management component of a database system implements the support for atomicity and durability. Example, the shadow database scheme. Shadow database scheme, assume that only one transaction is active at a time. A pointer called db pointer always points to the current consistent copy of the database. All updates are made on a shadow copy of the database, and db pointer is made to point the updated shadow copy only after the transaction reaches partial commit and all updated pages have been flushed to disk. In case of transaction fails, old consistent copy pointed to by the db pointer can be used and the shadow copy can be deleted. See, this is the picture for that. This is shadow database scheme. Here the initially picture A, before the updation, the consistent copy of the old database. Okay, that is pointing to the old copy of the database. Now when you are starting the transaction, then you are going to make a copy of the original database, and you are going to make all updations to that old copy of the database. See, within brackets to be deleted, there is written like to be deleted, and that is the copy of the database. Initially db point is pointing to old database, and we have another old copy of the database to be deleted. That means when you are doing a transaction, you are going to make all adjustments or all updations in this to be deleted database, and once that is completed, then that is copied to, or the db pointer make the db point to the new copy. Okay, so once it is committed, when you are committing that, then the new, it will point to the new copy of the database, and old copy of the database will be deleted. Okay, that means initially the db pointer was pointing to the old copy of the database. Now what you are going to do is you are going to create a new copy of the database and make all updations to that new copy of the database, and once once a transaction is committed, now make this db pointer point to the new copy of the database. Okay, this is the way you are going to implement atomicity and durability. So here the problem is assumes disk not to fail. If there are disk failures, then there are problems. Now this shadow database scheme assumes that disks do not fail. This is useful for text editors but extremely inefficient for larger databases. Executing a single transaction to create a copying of the entire database, that is a very difficult problem. That means every time if you are going to do a transaction, you have to make, or you have to make a copy of the old database to new copy. This not a very good idea, but for smaller databases that is possible. Now concurrent execution. Multiple transactions are allowed to run concurrently in the system. Advantages are increased processor and disk utilization. Actually, in your railway database or in your K2 database or whatever database you are using today, they are supporting concurrent execution of thousands of transactions at the same time. So increased processor and disk utilization leading to better transaction throughput. One transaction can be using the CPU while another is reading from or writing to the disk. Reduce the average response time for transaction. Short transaction need not wait behind long ones. Concurrency control schemes. So these are the main points as far as transactions are concerned. Then in the next class, in the coming classes, we will discuss concurrency control schemes and serializability. Okay.